Burns right outside. Okay. Uh, so here, I'm going to see if I can jump to the answers, and the live class is going to call me out if I make mistakes and stuff. Draw and label all the forces acting on the crate. Okay, so there's a rope with a force of tension. There's, of course, mg. That's okay for gravity going down. There's going to be a normal force. The normal force should look like it's less than mg. Let's make mg look a little bigger. And if it's moving this way, I assume that's some sort of velocity, this arrow right here. Good job, College Board. There'll be a force of friction. Okay, and I can even, whenever I have some friction, I like to write down mu times F sub n, just to remind myself. Okay, I did it. Any other forces? Sure. Oh, I will. Hold on. It just says label them. So, great question. Do you have to start writing equations and stuff? Because I started to do this one by habit. No. You just label them correctly. And these are the standard labels. You could put F sub big G or little g. Everybody knows what G is. But any reasonable physics label. Okay, you can even put capital N for normal and lowercase f for friction alone without the force. But I like capital S for forces everywhere. Reminds me of stuff. Look, they're doing it too. College Board will often say, write force vectors, not components. So you can actually, notice how I didn't split this into cosine and sine. You can lose points for splitting into cosine and sine. Usually just 1 point. Okay, compute the normal force. The normal force is mg minus ft sine theta. Because then I would need that vertical component, and that's lifting part of the weight of the block. The normal force is just like the structural force of this floor. If you set something on the floor, it's solid, it doesn't break, it doesn't sag, it resists, and it resists with exactly as much force as is needed to lift. Okay, compute the acceleration of the crate. Compute. Um, so actually, if that's all I wrote for part B, I would be in trouble because it says compute or calculate. So I would really need to start with like AY equals 0 because it's pulled across the floor horizontally, and then I have to derive it. So, but in the interest of time, I'll show you how we would compute. The acceleration of the crate is the net force, the total vector forces. Okay, and we would just be doing x because we did y, so I don't need to double that up. But we sum of the forces in the x direction divided by the mass of the crate. Okay, so then that's going to be plus, we'll make that the positive direction. It's pretty obvious that you don't have to do that. Right is positive unless they tell you otherwise. It's plus ft cosine theta minus the coefficient of friction. I needed that somewhere. I knew I was going to need it. Minus friction times the normal force, which is mg minus ft sine theta. Okay, and then all of it divided by the mass. Don't forget this. Okay, compute the acceleration. Are there any other forces? I don't think so. Let's see. I would want to simplify it though. Let's see. We have ft over m, and then cosine theta minus mu sine theta. And then we have minus mu g. Okay, any questions? That's part C. Very good. Assume the magnitude of the tension is fixed, but the angle may be varied. For what angle would the resulting horizontal acceleration of the crate be maximized? Oh my goodness. A max. Does it have a simple answer? Can we calculate it? Should we take derivatives? Let's see what they say. This doesn't come up a lot. I could solve for ax equals 0. Would that be the simplest? 1, 0. It would depend on what mu is. Because if I move the terms, you know what, let's do that real fast. Let's get the sines and cosines all to one side. Oh, that doesn't help very much. Cosine theta minus mu sine theta equals mu mg over ft. Oh no, I killed my a. Nope, I'm still stuck. What is this? Gravity, nope. Nope. I could have paused the thing. Almost. Momentum's balance, center mass. Hooray. And that's not even the answers. Wow. Okay. Chapter. Okay. There it is. Okay. Yes. In order to maximize the crate's acceleration, we want to maximize the net horizontal force. Well, yeah. They are all fixed. Maximize the force defendants. Maximize. Oh, I missed a negative sign. It's negative, negative, so it's plus mu cosine. Right? Negative mu, negative. Yep. Yep. Oh, dear. We really do. We take the derivative. dA d theta. At least that gets rid of that. And we set it equal to 0 to describe minimum and maximum. Have you learned this in calculus yet? That's an application of derivatives? Yes? Or no? Okay, some people know. Alright, don't worry about it then. That's not on your first test in here. But we can take the derivative of this, and it says on your equation sheet how to take the derivative of sine and cosine with respect to the stuff that's inside. And we just have a theta inside, so that's really easy. So you grab your equation sheet, write the derivative down, and then set it equal to 0. But if you're not that far in calculus yet, don't worry. All right, fantastic.